Chapter 2 is mathematical statements, and mathematical statements are used in such applications as contract law. They're also used in computer programming and other forms of technical writing, so they're not limited to only proof writing and other mathy situations. So let's take a look at some problems involving mathematical statements. Number one, is x is less than 2 a statement? Remember, in mathematics, a statement must be either definitively true or definitively false. In this case, we do not know what x is. X is a variable, and statements that have one or more variables are called predicates. So technically, this is not a statement. This is a predicate in the mathematical sense. Number two, negate the statement x is less than 2. Well, if x happens to be less than 2, let's say we know the value of x, and the statement would be true that x is less than 2, then the opposite of that, or the negation, would be x is either equal to 2 or greater than 2. So if you negate the statement x is less than 2, you would say that x is greater than or equal to 2. Number 3, negate the following statement. For all x values, x is greater than or equal to 7. Well, the first set of parentheses contains what is known as the quantifier. So here we have the quantifier for all. And the second set of parentheses gives us the predicate. X is greater than or equal to 7. The opposite of the quantifier for all is the quantifier there exists. So we would have to use there exists in x in order to negate the first part. And to negate x is greater than or equal to 7, we would simply say that x is less than 7. So remember, to negate a statement of this nature, we do have to negate both parts. We have to negate the quantifier, and we have to negate the predicate. Number 4, convert the following statement to an equivalent statement that uses the universal quantifier. Remember, the universal quantifier is for all. The statement says -1 is the largest negative integer. Notice this is rather concise. We're working with negative integers. So x cannot be just any number here in our statement. If we use the universal quantifier for all, we would say that for all integers less than 0, x has to be less than or equal to -1. For all integers that are less than 0, which means for all negative integers, x cannot be larger than -1. Number 5, negate the following statement. For all x, for all z, there exists y, such that x plus y is equal to z. And here we have multiple quantifiers followed by a predicate. We have the quantifier for all x, and then we have a second quantifier for all z, and we have a third quantifier. There exists a y, and finally the predicate, x plus y is equal to z. And again, as before, we must negate all parts. So the negation of for all x would be there exists x. To negate for all z, we would say there exists z. And then to negate there exists y, we would go after the for all y. And then finally, to negate the predicate, we would say that x plus y is not equal to z. So we would read it like this. There exists an x, there exists a z, such that for all y values, x plus y is not equal to z. Number 6, identify the free variables and the bound variables in the following statement. The statement says for all z, there exists a y such that x plus y is equal to z. Notice here that x is not bound to any quantifier. But if you look at z and y, z is bound by the quantifier for all, and y is bound by the quantifier there exists. But notice x is not bound. So here, x would be a free variable, whereas z and y are bound. Number 7, express A as a subset of B as a universally quantified statement. If we use the universally quantified statement for all, then we would basically say for any element x in A, that element must also be in B, set B. Number 8, convert the following statement to an equivalent statement that uses there exists. The statement says, some months are cold. Well, here I'm going to let M represent the set of all months, and we'll let lowercase m represent a particular month or months that happen to be in the set. We would simply say there exists an M that is an element of M, capital M, such that lowercase m is cold. In other words, if there exists a month inside of the set of all months, such that that month is cold. Number 9, change the statement, if x is a positive integer, then x plus 1 is a positive integer. They want us to change that to a quantified statement using for all. Again, we want to be as precise as possible with our language, and notice that they're keeping us somewhat confined to the set of positive integers. So we need to make sure that when we write our statement that we use the phrase positive integers. So here's what we would say. For all x's, for all values that are elements of the positive integers, then if you add 1 to that value, you are still going to be an element inside the set of positive integers. So for all x in z plus, x plus 1 is an element of z plus. And number 10, what is the negation of some mathematicians are not smart? Well, the word some implies that at least one mathematician is not smart. So the opposite of that would be that no mathematicians are smart. So we would say all mathematicians are smart.